Okay. Also, we have the information from when we have exploded nuclear explosions about how they are transmitted through the crust of the Earth as well. So seismic waves consist of two different types. You have your P wave and you have your S wave. These are longitudinal compression ones. This is a type of compression going in and out like that. And these are the fastest wave. And these move through surface rocks and interior solid liquid materials, right? The S wave goes in this direction, right? The snaky type of motion. This is the second fastest, and it does not travel through liquids, okay? The up and down of the crest and trough wave. These are surface waves, much like water waves. It's the slowest of the three, and this occurs where either one of these reach the surface. Okay, so that you have your P wave, S wave, up and down crest and trough wave. These are the ones you think of them like as if it were the up and down buckling on a surface. Okay, slowest, second fastest, fastest. The Earth's internal structure, we've got the internal core, outer core, and then the crust, and then the mantle, right? So this is the mantle back in this area. This is the core. The core is what we were talking about being made up mostly of the iron and all of that. The mantle is much thicker than that. A lot of it is iron, but then you start to get some of the silicates in there, and then you have your outer crust material as well. The crust covers the entire Earth. You have an oceanic crust, much thinner. It's basaltic rock, and it's denser, okay, right here. And you have your continental crust. So that these go about at the same level below the surface, so that the mantle is fairly regular in terms of depth. Well, in terms of radius from the center of the Earth. The continental crust is granite rock and is less dense. The Mohorovic discontinuity is where the difference, where these occur, right? At that point right there, okay? So when you have that, the seismic wave velocity increases sharply as it goes from crust to mantle. Okay? The discontinuity is all along here. This is the discontinuity right here, where it goes from crust to mantle. The thick shell between the crust and the core is the mantle. It takes up 80% of the Earth's volume, 2/3 of the Earth's mass. This is, as I said, iron, magnesium, silicate type of materials. And we know about it from 3 different data sources, seismological data. We've also examined meteorites that have hit the Earth and material ejected by volcanoes that pull things out of from there that consist of materials that came from down below here. And the balzac core is closer to silicate composition, chemical composition of stony meteorites. Okay. The core one, right here at the very, very center of the Earth, makes up 15% of the Earth's volume, 1/3 of the Earth's mass. So it's a very, very dense unit here. Okay. And then if you have the P wave seismological data, the P wave is refracted by the core, produces P wave shadows. Okay, no direct P waves seen between 103 and 104 degrees of the arc of the earthquake. So something happens right here. Okay, in this particular part right here, you're not going to get that P wave. It'll happen here, and then it'll happen here where it goes through the core. Okay. Of course, it does decrease with distance as well. And this is what has been used to calculate the shape and the size of this core. Okay? And this is the source of our data, is sending these waves through there. Then we have S wave seismic data. This is a larger wave shadow. Okay? So it's nothing occurs from S wave here. It only occurs up down to that 103 degrees, as you saw from here. So the P waves and the S waves both will cover this area. P waves will also cover this area, not here and not here. S waves will cover only this exterior part out here. Okay, the core acts like a liquid, not allowing this to propagate. So what this says is that the liquid has this portion right here is a liquid outer core and a solid inner core. And this is supported by both the S wave and the P wave data. Other core things that support this information are iron meteorites that we have seen that have come from, that have impacted on the Earth. They're mostly iron or the iron-nickel alloy. They're thought to mimic the chemical composition of the core. That's a theory. There's some there's some information that backs that up from the different seismic data. Earth's magnetic field also helps support that. The source is a turbulent flow within the liquid core, so the material must conduct electricity. The meteorite and magnetic field data are consistent with an iron core. So the data is consistent with that. But until we actually tap down there, we haven't proved it exactly. More detailed structure is the asthenosphere. This is a thin, hot, elastic, semi-liquid layer in the upper mantle and is distinguished by the sharp decrease in the seismic wave velocity. Okay, you can see that right here, right at that level. The lithosphere is a solid layer between the asthenosphere and includes the entire crust. The moho, this is the morphogenic discontinuity, and the upper mantle, and it's made up of rigid plates floating on the upper mantle. Okay, so this is what they're talking about up there. This right here. This is the lithosphere. Okay, individual continents shift positions on the Earth's surface. This is a theory. Okay, it is a theory that this initially fit into there, and that this was over to here as well. And it's possible that there is some degree of fit there. And this is the original concept of continental drift, of things moving one way and another on here. That's a theory, okay? Until you have actual facts where you can, the continental drift does occur. The theory of plate tectonics is still a theory. There is evidence from Earth's magnetic field of igneous rocks recording the magnetic field strength and direction. The magnetic poles lock into alignment with Earth's field upon crystallization. Earth's magnetic field varies in strength and direction over time. There have been 22 reversals over the past amount of time. So, well, I don't, the timing on this is another very important thing in terms of it's a hypothesis of something that has taken place in terms of that time. The timing on that is something that we have yet to determine exactly and scientifically, as far as I'm concerned. But what there have been is that there have been 22 reversals that we know of. The exact time frame is open to question. Evidence from the ocean ridges, okay, coincide with submarine earthquakes. Submarine here does not mean that it means below the ocean level. That's what submarine means in this particular case, not some little vessel where a bunch of sailors are. And there are rifts along a crest. Large amount of heat escapes from the crest, and there's this mid-Atlantic ridge right here. There are also long, narrow, deep troughs with deep sides, these trenches. They always run parallel to continental edges. And the seafloor is spreading, and we can see that there is some spreading that has taken place. the thin sediment layers near the ridge become thicker towards the continents. Older fossils and rocks near the continents become younger near the rifts. Again, fossil dating is another subject of contention on that. A hot molten rock moves up from the Earth's interior, emerging from the rift. And the reason why I say it's something that is because it's a cyclical thing. They date the rocks from the fossils, and they date the fossils from the rock, and that's circular reasoning. It doesn't prove as much as I think they think it proves. The magnetic sea force spreading is also evidence of the shifting. I mean, this does happen, and we are seeing this take place. We know that it's occurring. The paleomagnetic patterns of the magnetic strips on the ocean floor and the basaltic rock. The identical magnetic reversal patterns on both sides of the ridge. The patterns match those found elsewhere, providing a match on those. So the basis of the plate tectonics theory has been shown. The lithosphere is broken into fairly rigid plates. That is definite. Plates move on the asthenosphere. That's how far down it goes. Earthquakes, volcanoes, and other rapid changes in Earth's crust are most often at the edges of these plates. And the three plate motions are divergent, convergent, and transform. Okay? There's a divergent, they're moving away from each other. Convergent, they're moving towards each other. Transform means that they are shifting along the plane. One's going up and one's going down. Divergent boundaries occur between two plates moving away from each other. Molten material rises to fill the fissures, and a new crust zone occurs. Example of this is the Mid-Atlantic ridge there. Convergent, two plates move towards each other. Old crust is destroyed in the process. And this is the continental and oceanic plates converging oceanic plates. And this is where you get a lot of the earthquakes and volcanic activity. And the ocean plate convergence right here is the trench and underwater ridges. And you can see that associated with deep-seated volcanoes, island arcs where the melted subducted material rises up from the seafloor through the overriding plate there. And then the continental continent plate convergence, less dense granite material rises up, resists subduction. Plates collide, pile up, produce a deformed, thicker crust here of lighter materials. And this is the examples of this have been the Tibetan Plateau and the Himalayan mountains. And then the transform is when two of they slide by each other, right? The crust is neither created nor destroyed. Irregularities and movements along the boundaries, sudden jerks produce earthquakes. The fault line across the California coastline is an example of that. Present-day boundary understanding. What drives the plates? The current working hypothesis is convection cells in the asthenosphere. Hot fluid materials rise at diverging boundaries. Some escape through the sea crust. Some work to the other ones and drag the other ones. There's little supporting evidence for this, and that's the end of that particular chapter. Chapter 19 is building the Earth's surface. So essentially what you're going to do is you're going to talk now about how those things are observed today in the scientific practice. And I'll start that with the next chapter, with the next section.